So this presentation is about research we've done to identify best practices for producing birch syrup with the best possible flavor and quality. And it was work that was supported by a grant from the National Institute of Food and Agriculture's Improving Food Quality and Value Grants Program. So to start from the beginning in terms of what is going to influence the flavor of the birch syrup that we produce, birch sap itself has a number of properties which are going to potentially impact ultimately what flavor develops when we process that sap into syrup. And first and foremost among these properties is its relatively low sap sugar content. So we tend to kind of throw around the concept that birch sap is about 1% sugar or half of what we expect maple sap to be. But in reality, in our experience doing research on birch sap collection and syrup production, what we've seen is that really the sap sugar content can be even much lower than that. This figure shows an example of birch sap sugar concentration in one year that we did research on the subject, and you can see that the average sap sugar concentration across that entire season was definitively less than 1%. It was about 0.66% in this study. So generally speaking, birch sap sugar concentration is very, very low, and that factors into potential flavor development issues because for many reasons, but one of them is simply that there has to be a great deal of concentration that happens to get that sap from sap concentrations to syrup density, or the solids concentration that we expect for syrup. So we have to do a lot of transformation to get that sap to syrup density, and that can impact ultimately the flavor that we are developing in the syrup. The second very important property about birch sap, which definitely impacts ultimate flavor development, is that the predominant sugar that's present in birch sap is invert sugar. And so the predominant and really the primary sugar in maple sap is sucrose. And sucrose is actually a disaccharide, which means that it's a molecule of two individual sugar molecules bonded together. So sucrose is actually a molecule of glucose and a molecule of fructose that are bonded together. And when we split those apart into their separate glucose and fructose, this is what we refer to as invert sugar. And invert sugar has extremely different properties than sucrose, and many of those properties ultimately affect how flavor development occurs. Another major property about birch sap that has the potential to impact flavor development is that it's relatively acidic. And we kind of tend to think of, oh, well, maybe birch sap is a little bit acidic because we're collecting it later in the season, so there's a lot of microbial activity which can indeed lower the pH. But the truth is that birch sap is quite acidic even when it's freshly collected from the tree early on in the season. So again, in that same study that we did in 2018, this is just a snapshot of the pH of that birch sap that we were collecting across the season. And you can see that even in the very beginning of the season, the first collections, the pH of that sap was below 6, so slightly acidic. And on average, at least in this year, it was on average 5.3, which is definitely slightly acidic. We find on average it's between 4.2 and 5.9, but this can vary greatly. And so it's inherently acidic, in part due to the presence of invert sugars. So glucose and fructose themselves can lower the acidity, lower the pH of a solution. There is a high concentration of organic acids in birch sap, which also contribute to the pH. And then, of course, as I mentioned, we do have a relatively high propensity for microbial activity because we're collecting birch sap later in the season when things are warm and there is a lot of microbial activity. And when microorganisms begin to consume something like birch sap, that can also lower the pH. The pH is something, the pH of a solution is something that can greatly affect the way that flavor development reactions can occur. And so now we can talk about, well, where, before we can understand how we make birch syrup with great flavor, what we need to understand is, well, where does syrup flavor in general come from? And generally speaking, whether it's maple syrup or birch syrup, the majority of the color, but also flavor of syrup is going to develop due to reactions that we refer to as non-enzymatic browning reactions. These are reactions that occur as these solutions are heated. And so generally we often sort of lump all of these together and call them caramelization. In reality, that is not true. Caramelization is a very specific type of non-enzymatic browning reaction. It is when sugars are heated in a dry condition and there is a loss of a water molecule. And so I'll talk about that in a moment. But the primary reactions that are occurring, whether it's in birch syrup development, flavor development, or maple syrup flavor development, are Maillard reactions. So these are reactions between reducing sugars and reducing nitrogen compounds that react to form a wide variety and diversity of flavor and aroma compounds, both good ones that we desire, as well as off flavors and flavors that aren't so desirable. And the second class of reaction that we often don't give really much of a thought about, at least in the general thinking, but they're extremely important in the development of maple syrup flavor. And this is just the thermal degradation of sugar. So what happens when sugars are heated in a liquid situation? And in fact, in maple syrup production, these thermal degradations of sugar reactions, so that don't require the presence of another nitrogen compound to make their magic happen, so to speak. These thermal degradations of sugars are responsible for some of the primary flavor compounds associated specifically with maple flavor. So they're extremely important. But when it comes to birch syrup flavor in particular, this setup is extremely important to pay close attention to, because those Maillard reactions are really the dominant sets of reactions, non-enzymatic browning reactions that are happening, that are causing color and flavor to develop when we process sap into syrup. These are reactions between reducing sugars and nitrogen compounds. So those reducing sugars include sugars like glucose and fructose. Sucrose itself is not a reducing sugar. So when it comes to maple syrup, this is why when we have really sort of pristine sap from trees that is predominantly sucrose, we don't have a lot of color and flavor development with that type of maple sap, because sucrose does not readily participate in these Maillard reactions, and in part basically needs to get broken down into its components before the Maillard reactions can really proceed at a good rate. However, with birch sap, here we already have glucose and fructose to start with. So we have those reducing sugars. We also know that there is quite a bit of nitrogen compounds going on in birch sap at this time, not just from the tree itself, but also potentially from the microorganisms that are very active in that sap, again, because we're collecting later in the season when there's sort of more activity in general. So just straight from the start, birch sap itself has a much greater potential from the starting gate to produce a wide variety of color and flavor compounds. And then the other thing to take note of is that while true caramelization true caramelization for a molecule like sucrose requires extremely high temperatures. Same really for glucose, but sucrose in particular. We will not see those temperatures in an evaporator unless it's a condition where, say, for example, you have some syrup trapped between niter and the pans. But as far as liquid boiling in the pans, that temperature is much higher than we should ever see in an evaporator. So true caramelization really isn't likely to be a strong contributor to the development of flavor in maple syrup. But you can see that the temperature for caramelization in fructose is much, much lower. And for that reason, caramelization comes into much greater play when it comes to flavor and color development with birch sap and syrup production. And this is important in particular because, well, all of these reactions have the potential to produce both good flavor and aroma compounds and bad ones, but caramelization in particular, we know from probably all of us from experience that when caramelization is taken to reasonable points, so the points that we're aiming it for, we develop lots of flavors that are really desirable. But as soon as it goes too far, we have burned charcoal. So all of these reactions, particularly the Maillard reactions, though, they are, well, all of them are extraordinarily complex. So the rate and directions of the reaction, so how fast they happen, what type of compounds they actually make, are going to be extremely diverse and variable and affected by the conditions in which they're taking place. So pH is a factor that is big in determining what direction these reactions go in, so what flavor compounds they make. The water content, so the way that these reactions proceed are going to happen very differently in the back pan, where water content is actually very high compared to right near the draw-off. Temperature, of course, is big, but also something to keep in mind is the specific compounds that are present will affect what happens. So, for example, glucose reacted with one amino acid, reducing amino acid, will make, and heat it together, will make one set of compounds. But if we heat glucose with a different amino acid, a different set of flavor compounds will be made. So just in kind of providing that broad overview, you can start to get the idea of just how extraordinarily complex these reactions are. And in many ways, we understand very, very, very little about them despite hundreds of years of studying this. Don't be shy about the fact that this is really complex and difficult to understand. But hopefully we can provide some illumination on some parts of it today that help us control the process, at least in the best way that we have available to us at the time. So when it comes to processing birch syrup and birch sap into syrup, so the question is, what practices result in the best flavor? And there have been a number of sort of debates and thoughts within the industry over time. And, the sort of natural inclination is that because we know that we have a high concentration of fructose, things that are going to produce color and flavor at lower temperatures, this sort of natural inclination is to say, well, we need to process the sap very slowly at low temperatures to prevent scorching and burning and sort of kind of prevent too much flavor development in the wrong directions. And that makes total sense. However, at the same time, we have producers that have been making birch syrup for a very long time who have found in their practices that really, in reality, to make birch syrup with the best possible flavor, you need to process it as hot and fast as possible. So you really couldn't get more different than that. And so that's been one of the questions within the industry over time is really, what is the answer there? Where is the balance point to produce syrup with the best flavor? Other questions are a little more nuanced and have to do with the fact that this is not maple syrup, so there is not currently an official standard of identity for birch syrup, and that opens up possibilities for things like, well, do we really need the solids content to be what we finish maple syrup to? So does it need to be around 66% solids, or could it be something lower than that, finishing to a lower density without those sort of late stage flavor development reactions that can really go very fast and furious as we are just finishing syrup in those last few concentration steps, potentially by stopping before we get there, maybe we'd produce birch syrup with even more desirable flavor. And then the thing that we need to sort of, I probably should have put it at the top of the slide instead of the bottom in parentheses, but the overriding thought that we need to keep in mind whenever we're addressing this question or trying to do research to address this question is, what is the best flavor when it comes to birch syrup. And generally speaking, what is the best flavor for just about anything is a very personal and individual assessment. What the best flavor is for any particular product is often more between our own individual ears than it is some kind of consensus among a great number of people. So that is something to keep in mind. Likewise, what is the best flavor for birch syrup used for one type of application may not be the best flavor for a different type of application. So birch syrup that is destined for culinary applications, so use in cooking and cuisine, the best flavor for that and those applications may be very different than the birch syrup that we are aiming to have as a topping for desserts or pancakes or something like that. So that is another thing to keep in mind. So with all of those looming questions in mind, the overall objective of this project was to do research to identify processing methods that produce birch syrup with the best possible flavor and quality. So really this project was aimed at finding methods to optimize flavor. But at the same time, we're collecting other data to sort of augment that and also assist us in producing birch syrup with the best possible flavor and quality. And those include things like developing appropriate tools to measure the solids content of birch syrup, since all of our tools that we're generally using now are calibrated for maple syrup and maple sap, which is predominantly sucrose. So we'll talk about that a little bit later on in this presentation. And then also we're collecting some data throughout this research on the basic composition and properties of birch sap and syrup. This is also to help us have best practices for producing birch syrup with the best quality, having a better understanding of the viscosity properties of birch syrup, as they are definitely different than those of maple syrup, having an understanding of what the water activity of birch syrup is like, which can affect its shelf life. All of these things can affect both the quality of syrup that we're putting in a bottle or a jug, but also how we and our consumers are going to be experiencing and perceiving the qualities and flavor of the syrup that we're producing. So all of this sort of goes into the pie to help us collect data to get information to help us produce the best quality and flavor birch syrup possible. So as I mentioned already, these are the major debates that had existed in the industry, and so these were some of the major questions that we were choosing to address first. And so we ran experiments for 2 years, and in the first year of the experiment, the major objective or questions that we were looking at was basically to begin to address those major questions that had already existed in the industry. So number one, is the flavor of birch syrup produced with low temperature processing techniques preferred over syrup produced with standard processing temperatures? So trying to begin to get at that question of, do we need to process this low and slow, or is hot and fast better? So we chose to look at low temperature processing in this first year. And then we also wanted to look in this first year of the experiment, is the flavor of birch syrup finished to lower than standard density preferred over that of syrup finished to a more standard syrup density, something closer to maple syrup? So trying to get to that question of, do we really need to finish this syrup to the density that we finish maple syrup to? And so the methods that we use to conduct this experiment are really pretty simple, and they're very similar to work that we've done with maple syrup in the past. And that is that we simply produce syrup simultaneously from the same birch sap material, in this case with and without air injection. And air injection is a process that bubbles air into the boiling liquid in the pans, in this case, in both the back pan and the front pan. And in doing so, although this can have other effects, the primary effect of air injection is to lower the temperature of the material in the pans. So this is actually a way for us to introduce a low temperature treatment in our processing conditions. And then we also, in the same experiment, finished syrup to both standard syrup density as well as to lower syrup density, around 60% solids. And so to do this, pretty simple, we obtained quantities or loads of birch sap concentrate. This year we were using about 6% birch sap that was concentrated to about 6%. And each time we would obtain this, we would put it into a single tank that is set up to feed both of those identical evaporators. And those evaporators are set up as identically as possible to one another. So they're set up and adjusted to have the same fuel rate, the same draft. We're using the same pan depths, the same draw off temperatures. Everything is exactly the same, except that one of them is equipped with air injection in both the front and back pans, which you can see at least in the front pans here. And this is just a closer up image where you can see the air injection sort of operating in the front pans. This is while we're still sweetening the pan, so there's it's still basically just 6% at this point. You can also see that we have probes in there to measure the temperature to make sure that we are actually achieving a lower temperature treatment compared to our control evaporator. And so what we're doing basically each time we run this experiment, we flood the evaporators with the same sap, start them simultaneously, and then allow them to run and process that sap material until it's finished, and until the sap material is done or exhausted. And so we are, while we're doing this, collecting and filtering all of the syrup produced by each evaporator separately. And this is at standard density, so using a standard automatic draw-off device. But then at the same time, to get at that density question, we're also drawing off syrup, not quite syrup, or material from the evaporators at a point before the draw off. So we have, I showed in the previous slide, there was a little tube, a stainless steel tube connected to this tubing, which is connected to a peristaltic pump, which runs constantly and draws off material from, and we have one of these in both evaporators. It's hard to see this one on the right, but we're essentially drawing off material from those evaporators at the same point. That is at that point it is approximately 60% solid. So we're collecting it into a separate container and filtering it separately. So in this way, we have not just our syrup produced with and without air injection from the same sap, we have syrup that's produced with and without air injection from the same sap, both at standard density and at this slightly lower than standard syrup density for us to look at. So we repeated this experiment on 5 different days during the birch syrup production season. And so just as I sort of outlined, on each date, we are producing 4 syrup samples, and again, all from the same source of birch sap concentrate. We have our control syrup at standard density, so produced in standard processing temperatures, a standard 3x10 evaporator. We have our syrup produced with everything exactly the same, except it was produced with air injection in the other evaporator. And then we also have our standard processing temperature and air injection syrups that were finished only to 60% solids. So at the end of each day, once these are filtered, we then pack them and freeze them for analyses at the end of the season. And once we are all finished and we have all the samples from that experiment, we analyze them for a great number of different properties and parameters. Everything from very simple things like color and pH and conductivity. We were measuring density or solids content in all of these syrups with a number of different methods, tools and methods. And the goal of that was to help contribute the knowledge that we need to develop tools appropriate tools for birch syrup to finish it at appropriate solids content. We also had it analyzed for water activity, viscosity, carbohydrate composition, and inorganic minerals, lots and lots of things. But today, the focus of this presentation is really all about the flavors. So I'm not going to talk about most of this today. This is a subject for other presentations and in the future, as well as some other written material that we have. But flavor is the focus. And there are 2 essential ways that we can analyze and investigate the flavor of syrup that we produce in our experiments. One is in some ways a relatively simple way, and that is to do a chemical analysis of which volatile aroma and flavor compounds are present in the syrup and in what quantities. And we do this with gas chromatography and mass spectroscopy. And we did do this for these syrup samples, and we have a wealth of data on this. However, I'm not going to talk about most of it today because in most situations, especially with a goal that we have for an experiment like this, where we're trying to identify how do we produce birch syrup with the best possible flavor, the most important and in many cases sensitive detector of differences and nuances like that in terms of what is the best flavor is really the human palate. And so the most really, in many ways, the most important analyses that we do are these sensory evaluation experiments with the syrup we produced in the experiments to determine, is the flavor of the birch syrup we produce with our low temperature processing treatment preferred over that produced with our standard processing temperatures? Is it preferred by real human beings tasting that syrup? And hand in hand with that, how about, is the flavor of that syrup we finished to a lower density preferred over the syrup we produced at standard syrup density? So human beings are the target of this research, and they are also really best equipped to give us the answers for this research. So to do these sensory evaluation experiments, the very first step that we need to do, first of all, is to de-identify the sample. So each syrup sample is given a random 3-digit code and then put into these opaque bottles. The opaque bottles are really important because as human beings, we inadvertently do a lot of our flavor evaluation with our eyes. And in this case, we're really interested in our flavor evaluation, that the flavor, the actual flavor of the syrup. And so in order to eliminate the potentially confusing or confounding impact of what we see on the flavor of the syrups that we are tasting, we need to make sure that the panelists in this experiment can't see the syrup. So they're using their taste buds and their noses and not their eyes to tell us what they think about the flavor of this product. And for these experiments, we had 45 sensory panelists that were recruited and pre-screened. They had to be healthy, non-smokers, and interested in birch syrup. So they had to basically be at least open to trying birch syrup and working with it and things like that. We did it in 4 different experiment sessions. And during each of these sessions, basically what we would do is present samples for 3 of the production dates in our experiments to the panelists in a randomized order. So each panelist is not just getting the samples from the 3 different dates in a different order, but within those dates, they're tasting them each in a different order. So no panelist is tasting any of these in the same order as one another, and that helps avoid things like carryover effects. If one syrup has a very strong flavor, it could influence the flavor of the next. By randomizing the order in that way, it eliminates or reduces the impacts of things like that on the results. So the panelists are asked to taste each syrup and respond to a single question about its flavor. And that was simply, how much do you like or dislike the overall flavor of the syrup? And they were asked to analyze this on a 9-point hedonic scale, a very standard scale, from dislike extremely to like extremely. And so they're asked to do this for each syrup that they tasted. And answering this question and having them answer this question allows us to get an idea to answer our 2 major questions. And that is, within each production date, is the flavor of the syrup produced with low processing temperatures preferred over that produced with the same sap using standard processing temperatures? And also, within those production dates, is the flavor of the lower density syrup preferred over that of the standard density syrup? So let's take a look at the results. So on this graph, what we have are the average liking scores for each of the syrups that we produced and tested on the 3 dates that we tested. And we're looking here at just the processing temperature results. So the syrup produced with low temperature processing, our control, or I'm sorry, low temperature processing, our air injection treatment, and our standard processing temperature, our control treatment. And so what you can see is, just visually speaking, you can see that there is not a huge difference in the liking, the amount that the panelists liked the flavor of the syrup produced with the 2 different processing temperatures on the same date. But what we saw was that from a statistical standpoint, on two of the dates, the flavor of the syrup processed with the standard temperature, so in our control evaporator, was liked slightly more than the syrup made with the same sap at the same time with that lower temperature air injection. And that was statistically significant on 2 dates. This is not highly statistically significant here, but this actually is. So this suggests that at least in a slight way, that the syrup produced with the lower temperature processing, our air injection, was slightly less liked, less preferred than syrup made with the standard processing temperatures. A couple of other things to notice about these graphs before that's the main finding, that's what we're looking for here. But some other things to notice are, well, number one, that the overall liking was relatively low. So it was the average for all of these samples, the average liking score was around neutral, neither like or dislike. And I'll talk about that a little bit more in just a moment. But the other thing that we can see, at least very general, is a trend for a decrease in the liking of the syrups as we go toward later production dates. And this is pretty suggestive that as our sap quality begins to decrease more and more, it's potentially having impacts on flavor that cause it to be less liked in general, regardless of what treatment we are using to produce that syrup. So I wanted to take a moment just to kind of tease out that average overall liking. So just looking at this average score for the 45 panelists for each of these syrups, it does look like, hey, they weren't really liked that much. It's average liking. But looking at average of a score like liking can really kind of mask some of the information about just what panelists were responding to with their answers for how much they liked the flavor of each of these syrups. So these are the averages of each of the categories on that 9-point hedonic scale for the control syrups and the syrups made with air injection. So even though we see if we just numerically average these scores, overall it's going to come out, it averages neutral. But if we look at the individual category responses, we can see that, for example, for the control syrups, about 50% of the responses were some kind of liked. So 19% of the panelists liked it moderately, 20% liked it slightly, 7% and 4% liked it very much and extremely. So there's a lot of panelists that liked this, and similar to with the air injection, so slightly less. So this is the overall average for all 3 of the samples that we tested. So on average, 47% of the responses were some kind of liking. So you can see 28% liked it slightly, 11% liked it moderately. So even though when we calculate the numerical average, it comes out neutral, you can see that that means that basically half of the panelists liked it in some way. So that's one of the reasons I like to show this, is that if you just look at that overall average of neutral, it paints a different picture than looking at this. Now, on the flip side of that, that does mean that about half of the panelists either were neutral to it, as in the case of the control here, 15% were neutral to the control syrups and 8% were neutral to the air injections. And that does mean that there were quite a few people that did not like the syrup that much. So everything from there was quite a bit more dislike in this quite a bit more dislike in the air injection than there was in the control. So over here, anything that wasn't liked is kind of dominated by that neutral category. Whereas over here in the air injection samples, we see not as much neutral response and more of the disliking. So again, that's just a little bit more of a nuanced way to look at how panelists were responding to the flavor of those syrups. So let's take a look now at the results for density, what they thought of the flavor of the lower than standard density syrups versus the standard density. And what we see, again, these are the average liking scores. And in this case, I've got the standard and low density for the control syrups and the air injection syrups all together on the 2 dates that were tested. And what we see is that there's no statistically significant difference in how much panelists liked or preferred the syrup or liked it. So basically, they liked all of the syrups, statistically speaking, in the same way, in the same magnitude. But you can see that when we look at standard versus low for our control and standard versus low density for our air injections, generally speaking, except for here, we see that most consistently that there's a slight tendency for the lower density syrup to be less liked. But again, that doesn't hold true here, so that's a little bit of a mixed bag. However, this is one of those cases where the math and the statistics tell me something on its own, but what tells me more than anything are the panelists themselves. And so in these sensory evaluation experiments, we allow we allow the panelists to give us comments on the syrups. They aren't required to do it, but they're given space for it, and we let them know that they can give comments if they like. And we received so many comments about the sort of unpalatability of that low density material that it really just sort of stuck out to me like a sore thumb that lots of the panelists were very off-put by the texture of that lower density material. So you can see some of them here: too thin, strange, too light, watery, weak flavor, not pleasant. So these comments tell me in some ways more even than the statistics do. There were a lot of people that it just was not a pleasant experience for. So the another piece of data related to that lower density treatment is when we looked at the water activity of those samples, the ones finished to about 60% solids, we saw that the water activity was quite high compared to standard density syrup. So it's over 0.8, which means, first and foremost, that it's not a shelf-stable product like we, in the same way that we consider maple syrup to be shelf-stable. So that lower density treatment also, was off-putting to many people, and also would present challenges at the packaging end of things. So that's something to keep in mind if you're still inspired to play with density. You will need to be very careful. There's nothing inherently extra shelf stable about birch syrup. Its water activity is high enough for things to grow if we finish it at that lower density. So in conclusion, what we found in this first year of the experiment is that the flavor of our syrup produced with standard processing temperatures seemed to be preferred slightly over syrup made with lower temperature processing conditions, in this air injection. And the lower density syrup was not preferred. It was not significantly different than the control syrup, the syrup produced with at standard density. And we saw many comments that really indicated that maybe it was really not so pleasing to the palate. So that was the end of the first experiment. With those results, we wanted to build on those results for the subsequent year's experiment. And so because we identified in year 1 that our low temperature treatment was slightly less preferred than our standard temperature, we wanted to explore that very hot and fast treatment. So the higher temperature treatment in year 1 was a standard evaporator. So we wanted to take it to the other end this in the second year by processing as hot and fast as possible. And to compare that, we wanted to compare it to as low and slow as we could go in a standard evaporator, but without any augmentation like air injection. So this was the setup for the second year experiment, really to explore whether, since we saw the higher temperature treatment in year 1 be slightly preferred, is going all the way, so super hot and fast, is that going to get us closer to where we want to be? So to do this, we actually simply set up our evaporators, our 3x10 identical evaporators. We adjusted their burners, their nozzles, and the settings for those nozzles in the draft to create those 2 different treatments. An evaporator that was designed to have super high fuel rates, be super hot, process super fast, versus an evaporator that had the tiniest nozzles you can imagine, so tiny fuel delivery rate, setting the draft so that things were extremely gentle, like as low as we could get it and still finish syrup at the other end. So 2 very extreme differences with the same evaporators, just using the setups of the evaporators themselves. And so to do this experiment, very similar to what we did in all of these experiments, really, we obtain a load of birch sap. This year, we opted to use a raw birch sap to make sure that the sap quality was as optimum as possible. So again, we're dealing with about 0.5% of sap sugar concentration. And so what that means or translates into a number of different impacts down the line, but one of them is that it took us 5 days to sweeten our pans. So we repeated this experiment on 9 different days. So each day we're obtaining a load of very fresh birch sap. We are starting the evaporators simultaneously and allowing them to process, one at super hot, incredible temperatures, and one as the slow, pokey one that's kind of like, just trying to catch up all the time. And then same as before, we're collecting the syrup from each evaporator separately, filtering it separately, and packaging it for subsequent analyses. And for this experiment, we ended up with just 3 pairs of syrup produced simultaneously with the same sap, using those sort of basically cool and hot processing temperatures. And same as before, we analyzed a great deal of parameters, including very detailed analyses of flavor. But in the interest of time, and because this is about flavor, this presentation is about flavor, I'm just going to talk about the results of the sensory evaluation experiments, just as I did with the last one. And in this case, we're doing a very similar setup, but we're trying to answer the question, is the flavor of birch syrup produced with low temperature, slower processing preferred over that produced with high temperature, faster processing techniques? So again, very similar to the 2017 experiment. The first year, we had 2 of the 3 pairs of samples that we produced during this experiment were selected for analysis. We assigned each of them a 3-digit code, a random 3-digit code, and placed them into the opaque bottles. And then for this experiment, we had 61 panelists, the same recruitment and pre-screening, so they had to be interested in birch syrup, healthy, non-smokers. And the samples were for the 2 production dates were presented to the panelists just as always in randomized order, both within and between those dates. And they were asked to taste and respond to the same question about flavor as we had in the previous experiment too. How much do you like or dislike the overall flavor of this syrup? And so in this case, we're trying to answer the question, is the flavor of syrup produced with higher processing temperatures, so hot and fast, preferred over that produced with those low and slow processing practices? And here are the results. Again, these are the average liking scores for our syrup produced with low and slow processes and hot and fast processes, on those same dates. So in this case, we have two dates, April 29th and April 30th. And what we can see is that on one of the dates, on April 29th, the flavor of the syrup produced with the hot and fast processing technique was preferred slightly, but significantly, over the syrup produced with the low and slow processing practices on that same date. The difference between these two, even though the average preference, the average liking was a little higher for the hot and fast syrup, it was not significantly different. Again, average liking was somewhere around 5, so that neutral mark, but when we look at the actual responses to the question, how much do you like or dislike, we can see not only some more information about each of the samples, but that in this case, there's a bigger difference in how much the higher temperature syrup was liked versus the lower temperature syrup on the same date. So over here, you can see that 62% of the panelists on that April 29th date liked that hot and fast syrup in some way. Lots of like moderately, some like very much, like slightly, compared to the low and slow syrup made, again, with the same sap on the same day. We see that only 43 of the responses were some kind of liking, a whole lot of dislike slightly, but still, we still have some like moderately and like slightly. So I think it's, again, important to look at these individual responses instead of just seeing that, you know, on average, they were somewhere in the middle. That really doesn't tell us as much as these individual responses can really tell us. So, but in this case, we see, you know, that was more than just really a slight difference in liking between that hot and fast syrup and the lower temperature syrup on the same date. So this makes one wonder what is different about those samples. And so I have colleagues at Agriculture and Agri-Food Canada in Ontario, and they have a really cool technique. So I mentioned before that we did do analyses of these syrup samples to analyze the presence of volatile flavor and aroma compounds. So this is the other way that we have to look at flavor. What Tim McDowell and Justin Renaud do is they take those results, the results of all the different volatile flavor compounds that are found in these syrups, which can often be just a gigantic list of unintelligible compounds that you can barely pronounce. But what they do is they link those compounds to known flavor and fragrance databases. So in other words, there are lots of databases in the world that link various chemical compounds with the flavors and aromas that they're associated with. So it's how we know that pyrazines are found related to cocoa flavors and things like that. So they take those two, link the chemical data to these libraries, and then produce these word clouds that both reflect not only what types of flavors and aromas are present, but also in what quantities. So bigger words here mean that those particular flavors are more dominant in the syrups. So it's one way that we can visualize flavor and aroma data, which can be very complex, in a way that is more digestible to normal human beings like you and me. So what we have here is the word cloud for those two syrups that were had a different preference, a significant difference in preference from our panelists. So here's the one made with low and slow, and here's the hot and fast syrup on the same day. So this is the chemical analysis of those two and reflecting the dominant flavors of those two syrups. And although on first glance, we think that maybe there's a difference. We see woody is bigger here, but it's also present here. Essentially, and you know, you guys have whoever's watching this, you have the luxury of just pausing this so that you can look at this for a long time. And when you actually look at these word clouds, what I see and what we see is that there is very little difference in the characteristic flavors and aromas that are present and the amounts that they're present. So we see, like, obviously dominated by sweet. We see caramelic in both. woody flavors and fragrances are aromas are slightly bigger in the cool. That could be something, but it's also quite present here. We see fatty as a more present. Fatty and waxy are more present in the hot syrup, which, as an aside, is very, very interesting because, as you might imagine, if we're processing hot and fast, we are having to use more defoamer to keep that material in the pans than we would in the low and slow. So we see that in the volatile flavor and aroma compounds. There is more defoamer in this syrup. I have no doubt about that. But from a flavor and fragrance sort of how is the flavor different, we really don't see anything jumping out at us that is a huge difference between the two. One potential reason for this is because those flavor and fragrance databases tend to be more heavily weighted towards pleasant aromas and flavors. So it's very possible that there could be a difference in the presence of a very off-putting off flavor that is perhaps present in higher amounts in the cool than in the hot, but we don't see it here because it's not part of a known flavor and fragrance database. So anyway, I thought I would include this because I think it's really cool, and because this is a recorded presentation, if anyone has something that they see in here that is a difference that stands out to them that maybe I didn't notice before, feel free to reach out to me and get in contact with me about that. Okay, so conclusions after these 2 years of our experiment. We do see a general slight tendency in both of those experiments for syrup made from the hotter treatments to be preferred. So this indicates that, there's certainly no compelling reason to go low and slow or use air injection based on the results of these experiments. What I think it does tell us is that when modifying a standard evaporator to modulate processing conditions, so either adding air injection or changing burner settings, about as dramatically as we possibly could, really didn't result in huge impacts on birch syrup flavor. So I think what we can conclude is that in many ways, with a standard maple evaporator, we have a limited range of adjustments to have major impacts on flavor, and I'll come back to that in a moment. The other thing I wanted to mention is just that drawing off at a lower density really did not seem to result in anything positive in the flavor department. So based on the results of these experiments, this doesn't seem like something to pursue for optimizing flavor and quality. But let's get back to that standard maple evaporator thing. So while we have limited ranges of adjustments to have major impacts on flavor, we do have a lot of things that we can do that will have significant impacts on flavor that come back to just best processing practices in general. So when it comes to what are our best practices for making birch syrup with optimized flavor, step number one is first to begin thinking about what you are making your birch syrup for. Who is your consumer? Who is your end user? And what is the optimum flavor for either that consumer or that product, that end use? So is this going to be for a culinary or a beverage application? Is it going to be used in cooking or making cocktails? Or is it going to be geared toward the secondary ingredient market? So are you going to be making birch syrup to sell to brewers to use in making beer, or sell to granola bar companies to add as a sweetener and flavor ingredient in their products? Or are you going to be making it straight for, you're going to want people to put this on pancakes, use it on ice cream, things like that? I think all of those things are very worth considering before you decide, well, what kind of flavor do I want to make in the end? So that's question number one. Who is our consumer? What is our product? And what is the best flavor for that application? And then we can do a lot to impact birch syrup flavor that just comes down to our basic other general best practices for producing syrup. One of the biggest ones is going to be sap quality. So our sap quality, in particular with birch sap, because it is we're already at a part of the season where things are warm, microorganisms are very active, and we already have an acidic product straight from the tree that could, can be worse and is already high in invert. Anything that decreases sap quality is going to affect everything down the line. We know that changes in pH are going to affect flavor development. Any kind of fermentation that's going on in the sap is ultimately going to affect flavor development and potentially quality. The less quality our sap is, the greater amount of foaming that we're going to have. That can lead to an excessive use of defoamer, which is going to affect our flavor. It can lead us to be more prone to burning and scorching from overflows. It's also going to ultimately affect our filtering efficacy, and that can have impacts on flavor, shelf life, and basic appeal. So I would definitely suggest that if your sap is looking like anything like this, you are probably going to want to address that as an issue. This is probably not going to produce syrup with optimum flavor and quality. So anything that you can do to maximize your sap quality is going to be key. And that can be everything from the basic best practices of processing it as soon as it is collected, to even more different, more advanced methods like finding a way to keep that sap cool until you process it. High levels of filtering can help, but they are never going to be the cure for sap quality that's as bad as this, for example. So these are things to be thinking about, but anything that you can do to promote sap quality is going to help result in better flavor, no matter what the processing practices you ultimately use. And other general best practices, again, this comes to us from, basic processing practices for whether it's maple or birch, but controlling the heat. So even though we see a slight tendency for the syrup made in these experiments with warmer or hotter processing temperatures to be slightly more preferred, we still have to be very mindful of keeping a handle on the heat. And that is not just because this can lead to a propensity to more easily burn and scorch syrup, especially with birch syrup, which we know not only has invert and fructose, so it's going to caramelize and burn at a lower temperature, but also remember that we are, especially if we're going with raw birch sap, we are going to be concentrating a great deal more than we would with maple syrup. That means that even without anything else, there is a potential for more niter to develop in our pans. And as we increase, so there are a couple of different interplaying issues there. So if we have just more niter in general, that means that we're going to have enhanced foaming, more trouble with scorching, et cetera, so potential for off flavors and processing issues there to begin with. But as we increase the heat, the niter that we're making is going to be adhered to the pans more, potentially causing us more issues, more foaming issues, problems with cleaning, and problems with cleaning often beget problems with chemical off flavors. So there's a lot of issues that need to be taken care of with respect to heat. So even though the temptation might be to go as hot and fast as possible, controlling the heat in a manageable way is still really important to optimizing flavor because of these other associated issues. And with birch, sap, and syrup, I cannot stress this enough, although it is absolutely essential to have food grade materials with no lead in all food production, maple syrup included, it is not just essential, it is critical, you cannot break this rule. For making and collecting birch sap and making birch syrup, it must be done in food grade materials with no lead or other heavy metals for that matter. Birch sap and syrup are extremely acidic relative to what we are used to dealing with in maple sap and syrup. The acidity of those liquids have a higher potential to leach contaminants from something like lead-containing solder or something we don't even know about yet. So it is extremely important to use food-grade materials, and food-grade materials are materials designed to be inert and not be able to have anything leach from them. So with birch sap and syrup, there's a no question deal breaker. You must follow these rules, even if you're just making it for yourself. And I strongly recommend having your birch syrup tested for lead regularly to ensure that, that it is a safe product and that you're not getting any inadvertent contamination. So other general best practices have to do with finishing to the correct density or solids content. As we saw with the results and some of those unsolicited comments from our panelists, density and finishing to the right density is and can be really important for how your consumer is going to perceive that flavor. So if you're going too heavy, if you're going higher than you need to go, you're going to be more likely to burn that or scorch that. Fructose is caramelizing at 230 degrees, or 220 degrees. So, you definitely don't want to go too heavy, but you also don't want to go too light. It could be off-putting to the consumer. The challenge with this when it comes to birch syrup is, and has been, as all of you birch producers know, that the relationship between sugar concentration and temperature, density, and refractive index is completely different for invert sugar than it is for sucrose. And all of our tools in the maple industry, our hydrometers and refractometers, and even our finish temperatures, our boiling point elevations, all of those are calibrated for sucrose solutions. So how do we do this? So as I mentioned, basically the problem begins with the fact that the density of invert and sucrose solutions, so the invert and sucrose solutions of the same concentration, percent sugar, are going to have different densities, not just at the same temperature, but they're going to differ at different temperatures. And the difference between them gets bigger at higher concentrations. So I'll show you something in the next slide that will make this make more sense. But the bottom line is that our maple hydrometers are going to underestimate the density of birch syrup. And the difference, the underestimation, is going to get worse the higher the temperature that you go. And so just to kind of show an example of this, and this kind of is a brain bender for me also, so this is maybe another great reason to have a recording so you can pause it and look at it, scratch your head. Maybe that's what I should do right now too. But anyway, so what we have here is the density of a 66% invert solution and a 66% sucrose solution. So 66% sucrose in water and 66% invert sugar in water. And this is the density of those solutions as a function of temperatures. So as you can see, as the temperature goes up, the density of both solutions go down. This is why we have to make temperature adjustments on our hydrometer. But what you can see here is that not only is the density of a 66% solution of invert and sucrose different just in general, but that difference gets bigger at higher temperatures and starts to change faster at higher temperatures. So what that means functionally is that definitely anytime we're measuring the solids content of birch syrup at anything but room temperature, things are much more complicated and less accurate. But for sure, when we get up into the range of where we're pulling material off our evaporator, things are going really crazy at that point. They change really fast with small changes in temperature, and the difference between what invert is doing at that point, birch syrup, and what maple syrup or sucrose is doing at that point is actually quite pronounced. So this is also, before I talk about that a little bit more, also the same case with refractive index. The refractive index of invert and sucrose solutions are different from one another, and they are different at different temperatures. So this, just as a visual example, this is my maple syrup refractometer measuring a sample of birch syrup. And this is the same sample of birch syrup in my invert refractometer, so a refractometer that is calibrated for measuring invert sugar solutions versus sucrose solutions like this maple refractometer is. And so you can see, same birch syrup, they are measuring, giving us different numbers. And this is at room temperature. And the differences are going to be bigger both at higher concentrations and at higher temperatures. But the same basic fact holds as for hydrometers. Maple refractometers are going to underestimate the density of our birch syrup. And so just to show you some real world examples here, these are the densities of birch syrup samples measured both with a maple and invert refractometer at room temperature. So this is the same birch syrup sample measured with a maple refractometer and measured with an invert refractometer. So you can see that for each of these samples, the maple refractometer is underestimating the concentration of invert in that syrup by about 1.5 percentage points. However, this is at room temperature, so the differences between what those two instruments read is going to get bigger and be more variable at higher temperatures. So anytime we deviate from room temperatures, things get a whole lot more complicated. And it's a very similar story with maple hydrometers. So this is same set of birch syrup samples measured both with a maple hydrometer and a specific gravity hydrometer that I've used to estimate invert based on known relationships between density and invert sugar concentrations. So what you can see here again is that the maple hydrometer is underestimating the actual sugar concentration in those samples relative to the invert hydrometer, which is getting it theoretically closer. So again, the difference here is on average about 1.5 percentage points, tends to be a little bit more variable than a refractometer just in general because of just the way hydrometers are. But again, as with refractometers, that difference between what a maple hydrometer shows you and what is actually there in terms of invert is going to get bigger the higher the temperature we go away from room temperature. And the same thing is going to come into play with our elevation of boiling point that we use to determine draw-off temperature. So we're all, at least the maple producers that are watching this, are probably used to the basic rule of thumb that if we want to finish maple syrup at approximately 67% sugar, that we are going to set our draw-off to about 7.5 degrees Fahrenheit above the boiling point of water. So in an example where water is boiling at 212 degrees, we know that we should set our draw-off temperature somewhere around 219.5. However, at that same temperature, the percentage of invert in solution at the same temperature, that's boiling at the same temperature, is only going to be about 63.4%. And so in reality, for a solution of invert sugar like we have with birch syrup, the boiling point elevation is probably closer to about 9 to 9.5 degrees higher. So in this case, if our water is boiling at 212, theoretically we should be setting our draw-off temperature to something closer to 221 to get a 67% solution. However, even this method when it comes to maple syrup can be quite imprecise, and as I'm sure many of you maple producers listening to this have experienced, this is not always the most reliable method, but it does, it helps kind of aim you in the ballpark. So when one of the reasons that it is can be imprecise is that these are boiling point elevations for pure sucrose and invert solutions. So anytime that you have a presence of an impurity that isn't sucrose or invert, if we're looking at birch syrup, that relationship between boiling point elevation is going to be altered from that basic rule of thumb. And the issue with birch syrup is that, again, remember, we've been concentrating this from a very low quantity. And for this and other reasons, there are numerous impurities in birch syrup, lots and lots of them. And in my experience producing birch syrup, I find that the boiling point elevation method is probably even, it's very, very imprecise and difficult to use to help me hone in to at least this rule of thumb. The 9 degrees is relatively not as useful as it should be. Certainly not as useful as the boiling point elevation for maple syrup. So what do we do to actually finish birch syrup at the appropriate density? Because all of these methods, not just boiling point elevation, but also the hydrometer, the refractometer, all of them are calibrated are set up to be used with pure solutions of invert sugar. Those are the relationships that define those and allow us to use them to estimate solids content or density are based on pure solutions. And those impurities that affect those relationships and make the measurements of those tools less accurate are really abundant in birch syrup, like I just mentioned. So we've got lots of organic acids, lots of minerals, potentially proteins, amino acids, other phenolic compounds. So in general, these tools are not just a challenge because we were trying to use sucrose tools for birch syrup, but also because of birch syrup itself. So, and this came and comes to light when we look at the actual carbohydrate content of syrup that we have finished. And so what this figure is showing is for syrup in one of our experiments. These are the refractometer readings with an invert refractometer, so well set up for using with birch syrup. And to the right of each one is the actual percentage of sugar when we analyze the composition of that syrup. So the actual carbohydrate composition of that same syrup sample. So what we can see here is that the invert refractometer for all of these is measuring somewhere around syrup density, so 68, 69, 67, and the actual carbohydrate content is significantly lower than that, 54% carbohydrates, 52%. What this is showing us is that the refractometers, and in this case also hydrometers, is reflecting the overall solids content of that liquid, of that birch syrup, but that there are lots of other non-sugar solids in that syrup that are influencing that measurement. So the actual sugar content of our birch syrup that we're finishing to what we're reading on refractometers and hydrometers at near syrup density is actually going to be much lower than that. So in this case, the difference is between 14 percentage points and as high as close to 20% of an underestimation, or sorry, an overestimation of the actual carbohydrate contents that are there. And so this is something very important for us to think about as we produce birch syrup, as we market birch syrup. So what do we do to actually finish birch syrup at our desired solids content? So even given that that disconnect between what our tools are measuring and what the carbohydrate content is, ultimately, it is solids content that we are aiming for to get us a product that is a similar characteristic to syrup. So we can use our hydrometers, our refractometers, and boiling points to estimate the solids content of our finished birch syrup product. We just need to be mindful that it's estimating solids content more than it is sugar content. So what I recommend at this point is to get an invert refractometer. These are, you can get a really nice invert refractometer that is, and actually if you go with a MISCO they can make a refractometer with both maple and invert scales. That's not a plug, but that is just a possibility, and the only one that I know of. If there are other companies that do that, that's great too. But get an invert refractometer. We know that that does a fairly decent job of estimating solids content of this syrup at room temperature. And you can, so what I would probably do just in practice is start by using a draw-off temperature about maybe 1 degree higher than for maple. So maybe 8.5 degrees above the boiling point of water for if you're aiming for 67%, and just dial it in. You will have a better idea. You will have a better idea once you are working with your syrup in your evaporator, how close or far this is from getting you to the desired point. You can use your maple hydrometer to see if you're in the ballpark, but again, we know that that underestimates density, and the hotter the syrup is, the more inaccurate it's going to be. So just as an example, at 211 degrees, if your maple hydrometer is reading that you're somewhere at 56, your invert solution is likely going to be closer to finished syrup. And this is interesting in practice. I'm sure many of you have experienced this because the properties of invert syrup and birch syrup are very different. It can appear or feel very thin when it is hot, when in actuality, once that cools down to room temperature, oh, wow, it really is 66.9% solids. But at 211 degrees, it may appear or feel very thin. And so once you have done this to sort of ballpark your way to the right temperature, then you can use that invert refractometer at room temperature to determine the final solids content. I absolutely do not recommend even having your refractometer in the sugar house. It's too tempting, and it is essentially totally useless and will be damaged if you're using it above 176 degrees Fahrenheit for sure, at least with this particular model and many others. But the temptation, of course, is there to put syrup on and allow it to cool, and so this is going to damage your instrument, and it's also going to produce totally erroneous measurements because that material is evaporating and cooling, evaporating and condensing. So you'll have no idea what's really being produced there. So take your refractometer out of the sugar house, use your other tools to estimate, get you in the ballpark of where you think you're going to go or where you think you are, and then use that invert refractometer later at room temperature to determine the final solids content. And that's one of the reasons why I said maybe aim a little lower, because ultimately, especially with most of birch producers at this moment, we're going to be repackaging, filtering and repackaging. So aiming a little lower gives you a little wiggle room to subsequently heat that up, refilter it, and package it at a closer density if you aimed a little low in the first place. That is just one suggested alternative, but I will be putting out some correction factors so that you can use a specific gravity hydrometer, but at the same time, because of that discrepancy between solids content and actual carbohydrate content, I'm not sure if it is going to be as useful to you as producers as simply getting in the right ballpark and then at room temperature using an invert refractometer to estimate the solids content. As for that discrepancy between our solids content that we're measuring and the sugar content, this is an issue for the future. So we definitely want to do some more research to confirm the consistency of this discrepancy. Is this happening all the time? Is this what we're doing in all sorts of different birch sugar houses? And is that disconnect between solids content that we measure with hydrometers and refractometers present universally? And in the meantime, birch producers need to be very careful with their advertising, with what they're saying is in a product, and also with nutrition labeling. You cannot use a solids content based on a refractometer or hydrometer reading to estimate the nutritional profile of the carbohydrate present in that syrup. So this is something to be very, very mindful of. And this is certainly something that the industry should be discussing in the future as this clarifies and we get some more data on it. So with that, I have a huge list of thank yous here. So make sure you spend a lot of time on this slide and read all of the people that helped make this project happen. And thank you for listening. For questions or comments, you can email me at the Proctor Center. You can find my email address at the University of Vermont Proctor Maple Research Center website. And I want to again thank the funding agency for this work. There is an extremely valuable and large amount of important information that we were able to develop from this project thanks to that support. And so if you know any USDA representatives, thank them too. Thank you very much. Bye-bye.